Hi everyone, and welcome to our second video. You can see here it says Notes Day 2 on solving differential equations and initial value problems. And the reason we're doing a second part is because today I've opted to choose a few more challenging examples of differential equations because they can come in all shapes and sizes, and it's good to have a variety. So let's just go right into it. This will look very familiar. If you look at example 1, we're going to solve this differential equation. dy dx is equal to x plus 3x squared divided by y squared, and we're given a point y of 0 equals 6, meaning that y is 6 when x is 0. So we'll use that condition to find our c. So the first thing we're going to do is we want to separate our variables. This is a separable differential equation. So I'm going to start, I'll highlight over top of this. And what I really want to do is get all of my x's to the right side and all of my y's to the left. So I'm going to start quite simply by multiplying both sides of the differential equation by dx. And that will clear my dx's out of the left side and give me dy equals x plus 3x squared all over y squared times dx. And then I want to get my y squared to the left side, so I'm going to kind of do the same thing. I'm going to multiply both sides by y squared. So this will give me y squared dy equals, these will cancel, x plus 3x squared dx. So I've separated my variables, all y's to the left, all x's to the right. So at this point, I'm going to integrate both sides because I'm trying to solve for y. So I have to get rid of this dy. So if I take the indefinite integral of y squared with respect to y, I get 1/3 y cubed equals, now if I integrate this side, I'm going to get 1/2 x squared plus x cubed plus c. Okay, now what makes this a little bit more challenging is we don't just simply have y equal. So we're going to have to do some work a little bit later to get y alone. But what I want to do first is find c. I like to find c right here. So I'm going to use my initial point up here, y of 0 equals 6. And I'm going to plug those values in right here. So my y is 6, so 1/3 times 6 raised to the 3rd power is equal to 1/2 times 0 squared plus 0 cubed plus c. And so this right side will just be equal to c. And this left side, if I take 1/3 of 6 to the 3rd power, I end up getting 72. So coming over here, I'm going to go back to this equation right here, and I'm going to add my c in. So I'm going to have 1/3 y to the 3rd equals 1/2 x squared plus x cubed plus 72. Okay, now all that's left, now that I found my c, all that's left is to solve for y. So first I want to clear this 1/3. So I'm going to multiply both sides of my equation by 3. And that's going to give me y to the 3rd. And now I'm going to have to distribute 3 over 2 x squared plus 3x cubed plus 216. And last but not least, I will just cube root both sides to get y by itself. So my final answer, y equals the cubed root of all this, 3/2 x squared plus 3x cubed plus 216. And that's going to be my final answer. So the same process as yesterday, just a little bit more involved. Let's take a look at example 2. dy dt equals t cubed y squared. So we've got a little product going on there. And our point, y of 2 equals 1. We'll use that a little bit later to find c. So let's separate our variables first. I'm going to start by multiplying dt to both sides, which will move that over cross those out. So I have dy is equal to t to the third y squared dt. And now to get my y squared to the left, I'm going to actually divide both sides by y squared. You don't have to show this, I'm just doing it for the notes right now. So this I'm going to write as 1 over y squared dy. And on the right side, I'm going to write it as t to the third dt. Separated the variables. Now I'm ready to integrate. Okay, what I'm going to do here on the left to integrate is I'm going to actually bring the y squared up and make it y to the negative second. And I'm just going to leave the right side alone. And now I'll use my power rule in reverse here to anti-differentiate. So when I add 1 here, I get a negative 1. And when I divide 1 by negative 1, I get negative 1. So I have negative y to the negative first equals. And when I anti-differentiate the right side, I get 1/4 t to the fourth plus c. Now, I'm going to clean this up a little bit. I'm going to rewrite this without the negative exponent as negative 1 over y equals 1/4 t to the fourth plus c. And now I'm going to go ahead and find c. So I'm going to use my green highlighting here. So I'm going to let the t be 2 and the y be 1. So negative 1 over 1 equals 1/4 times 2 to the fourth plus c. So this gives me negative 1 equals 4 plus c. And when I subtract my 4 over, I'm going to get that c is negative 5. So going back to this equation right here, I'm going to plug my c in. So I've got negative 1 over y equals 1/4 t to the fourth minus 5. And now all that's left is to solve for y. So what I'm going to actually do here is multiply both sides by y, which will cancel these out and give me negative 1 equals y times 1/4 t to the fourth minus 5. And to get y alone, I'll just divide both sides by 1/4 t to the fourth minus 5. And that should do it. These will cancel. So my y is equal to negative 1 divided by 1/4 t to the fourth minus 5. Now, some would say not to leave your answer like this because you have a complex fraction. So what you can actually do to get rid of that is multiply each term by 4, which will clear the 1/4, leaving you with a final answer of y equals negative 4 divided by t to the fourth minus 20. That's a nicer answer without the complex fraction. Okay, moving on to example 3, just cruising right through here. We've got a lot going on here, so let's just start by separating our variables. Let's multiply both sides by dx, which will give us dy equals 2x times 1 plus y squared e to the x squared dx. And now I want to get my y to the left, so I'm just going to actually divide this whole side by the binomial 1 plus y squared that kind of moves as a unit. Cancel these out, and now I've got 1 over 1 plus y squared dy equals 2x e to the x squared dx. I'm going to integrate both sides. And here's the deal. On the left, you have to look at this. This should look familiar from a previous unit. There was a trig function, an inverse trig function actually, that when you took the derivative, it looked like this. And that inverse trig function is inverse tangent y. And the reason is, if I grab a piece of scrap paper, if you remember this rule, it said the derivative with respect to x of the inverse tan of u is equal to 1 over 1 plus u squared times du dx. That was the rule from a previous unit, our derivative unit. Well, if you're taking the derivative of the tan inverse of, actually this would be d dy. If you're taking the derivative with respect to y of tan inverse y, following the rule, it would be 1 over 1 plus y squared times 1, which is just 1 over 1 plus y squared. So see this? That's exactly what we had here, and that's how I know the antiderivative is tan inverse y. Now on the right side, I see 2x e to the x squared, and I notice that the derivative of x squared is 2x. So this is actually my e to the u backwards. So if you remember, the derivative with respect to x of e to the u is e to the u times du dx. So the derivative with respect to x of e to the x squared is e to the x squared times 2x. So if you take this in reverse, you're just back to e to the x squared. So that's what I've got, and I'm going to add a c. Now this particular example did not give me a condition. It didn't give me an ordered pair. So that means I can leave c as is and just simply solve for y. So my last step here, well, to get y alone, I have to get rid of inverse tangent. And the trig function that gets rid of inverse tangent is tangent. So I'm going to take the tangent of both sides. The inverse tangent and the tangent will cancel, leaving me with y equals the tangent of the quantity e to the x squared plus c. And that is going to be my final answer, solve for y. And we flip it, and we've got 2 to go. We're almost there. Okay, example 4, dy dx equals 0.3y, and we've got a condition. So highlight these. And just like I always start, I'm going to separate my variables. So I'm going to multiply both sides by dx, which gives me dy equals 0.3y dx. Now I want to get the y to the left, so I'm going to divide by y. This is going to give me 1 over y dy equals 0.3 dx. And I'm ready to integrate. Okay, another blast from the past right here. I want you to think about this derivative. Remember the derivative with respect to x of the natural log of u? The answer to that was 1 over u times du dx. So the derivative with respect to y of the natural log of y would just be 1 over y times 1, which is 1 over y. Well, 1 over y is what I have right here. So to go backwards, I know the antiderivative of 1 over y is the ln of y. Now, when I do this, there is something I have to do technically. When I put the ln of y, I have to put absolute value bars around the y to indicate that you can only take the natural log of positive numbers. No matter what exponent you raise e to, you're always going to get a positive y. So this ensures that we know that. So the ln of the absolute value of y equals 0.3x plus c. Okay? Now, I'm going to go ahead and find c because I do have a condition. So I'm going to let my y be 1. So the natural log of the absolute value of 1 equals 0.3 times 0 plus c. This side just becomes c. The natural log of 1 is 0. And you can type that in your calculator, or if you don't have a calculator, you know that the natural log of 1 equals 0 because e raised to the 0 power is equal to 1. Oops, sorry about that. The natural log of 1 is 0 because e to the 0 is 1. Okay, so we have c equals 0. So going back to this form, we now have the natural log of the absolute value of y equals 0.3x plus 0, which I'm not even going to write. And so to solve for y, I would have the absolute value of y equals e raised to the 0.3x. And now that I'm in this form, I can drop the absolute value bars because e raised to any power, positive, negative, or 0, will always result in a positive y value. So y equals e raised to the 0.3x will be my final answer. Okay, last example, example 5. dy dx equals this quotient. There's no condition, so I'm going to leave my c as a c. So I'm going to start, multiply both sides by dx. So I'll have dy equals negative 2xy divided by 1 plus x squared dx. Now I've got to get that y separated into the other side, so I'm actually going to do this. I can write this as negative 2x over 1 plus x squared times y times dx. So I can pull that y out to the side because if I multiply these two, the y would just go right back up. Now I can divide by y to cancel those and divide by y over here. So 1 over y dy equals negative 2x divided by 1 plus x squared dx. I'm going to integrate both sides. Now, we just showed in an earlier example that the antiderivative of 1 over y with respect to y, remember up here, is the natural log of the absolute value of y. So I'll put that in. And this will equal, now over here, I've got to think about this. I see that I have the 1, like the 1 plus x squared on the bottom. This is very similar to, no, never mind. I must be thinking of something else. So let's take a look at this. What I notice here is 1 plus x squared, its derivative is showing right here, 2x. So I'm feeling a u substitution coming on. So I'm going to go off to the side and do a little work with u substitution. So if I let my u be this guy, 1 plus x squared, then my derivative of u with respect to x is going to be 2x. When I multiply both sides by dx, I'm going to have 2x dx. And when I solve for dx, I'm going to have du over 2x. So when I come back here, I'm going to actually pull this negative out to the front because it's a constant. And on the inside, I'm going to put my 2x over my u times what dx is, which is du over 2x. And that's exactly what I wanted to happen. I wanted these 2x's to drop, which now gives me the ln of the absolute value of y equals the negative antiderivative of 1 over u du. Now check it out. Because I've made this more simple, see how the antiderivative of 1 over y is the ln of y? Well, the antiderivative of 1 over u is the natural log of u. Bring the negative down, add the c, and bring the left side down. Okay, now I don't have to find c, so I don't have to worry about that, but I want to plug my u back in. So let's make this the natural log of the absolute value of y equals the negative natural log of u, which is 1 plus x squared, plus c. And now I'm going to solve for y. So I know that e raised to all this over here equals y. So I'm going to do that next. So absolute value of y equals e raised to the negative ln of the absolute value of 1 plus x squared plus c. And e to any power is going to be positive, so I'm going to drop the absolute value bars and just write it like this. Now, you would think you're done here, but I'm actually going to go one step further. My laws of exponents tell me that when I add two exponents, they must have originally looked like a product rule. In other words, I could rewrite this like this. Y equals e to the negative ln of the absolute value of 1 plus x squared times e to the c. Because when you multiply like bases, the product rule says you add exponents. Well, this right here, e to the c, is just a constant, because a constant raised to a constant is a constant. So the way in calculus we write this final answer is this constant we call capital C. We bring it to the front, and then we rewrite e to the negative ln of the absolute value of 1 plus x squared. And this is my final answer. So lots of different examples here, more challenging examples with differential equations. Hopefully that made sense. Thanks for watching.